Hi folks, we are back at section 2.4 studying a class of probability distributions called the exponential family. So let's just get started. I'm going to give you a little bit of, we're going to go through the first paragraph about what they're all about. And then I thought it would be really useful for both of us, actually, for all of us, to look online a bit as to why this family is so important. So I've used members of this family. I've never used it, I've never kind of worked with the exponential family as a whole. So I'm kind of learning and relearning some of this stuff with you. So yeah, I thought it'd be really cool. We'll just discuss a little bit in this video of just the basics of what they're about, and then we'll go to Wikipedia and also a conversation I have with ChatGPT about why they're so interesting. Okay, so let's get started. So the probability distribution that we have studied so far in this chapter, with the exception of the Gaussian mixture, that was the last one we studied, are specific examples of a broad class of distributions called the exponential family. And members of this family have many important properties in common, and so it's illuminating to discuss these properties in some generality. So basically all the ones we've seen, so one of the first aspects you're going to see is that many of the distributions we've been working with, exactly as he says, and many others, are going to be part of this family. So for no other reason than just kind of having a unified way of dealing with them, without having to deal with individual members, it might be useful to know about this family. But it turns out they have lots of other cool properties that we're going to discuss. Okay, but let's see what they look like. So the exponential family distributions over x, so this is x your data, given the parameters eta, is defined to be the set of distributions of the form. And notice that there's some term that just has to do with x. There is some term out here, this is an important one, that has to do just with the parameters. And then the parameters and the data interact inside the exponential. And interestingly, and it's one of the key properties, they interact via this function u. And we're going to be talking about that function u extensively. It's going to be really important. So the data, as you'll see when you're kind of trying to optimize the parameters, the data is not going to interact necessarily directly, but only via this function u. So that's going to be really important. Okay, so an x may be a scalar or a vector, maybe discrete or continuous. So the family actually includes discrete and continuous random variables. Eta are called the natural parameters of the distribution, and u of x is some function of x. And it says this function g of eta can be interpreted as a coefficient that ensures the distribution is normalized. Yeah, so the point is that you want this thing to integrate to 1. So if you didn't have this g eta, this function of g, this function of eta, then it won't integrate to 1. So you just think of it as a normalizing constant. But again, it's very special. Like it will have some, for the exponential family, these normalizing constants have very useful properties that we'll touch on. Okay, so I think at this point, why don't we? So we're going to switch gears, and we're going to go first to Wikipedia, and I want to highlight some of the really particularly striking example in properties of the family. We won't go through everything, but just some of the key points that I thought were interesting. So let's do that. Okay, so here we are. Okay, so we've just talked about the exponential family. So one thing is one of the very first properties of why it's so useful is so many of the distribution, the probability distribution we work with are in this family, and we'll see that also in the book chapter. But for example, here's like the normal distribution, classic example, the exponential distribution, the gamma distribution that we've seen. Beta distribution we saw way back when, the Dirichlet distribution, Bernoulli's, we've seen these. We've just recently talked about the Wishart and the inverse Wishart, etc. So all of these are kind of falling in the same framework. So you can kind of think of, if you know about the exponential family, you kind of somehow can work in the same way with all of these. Yeah, there's kind of a slight caveat here that there are others that are also in the exponential family, but only when certain parameters are fixed and known. So the point with the exponential family is that the parameters, yeah, so there's an aspect where, let me see if I already said it at the top. Basically, the domain can't depend on the parameters. So what do I mean by that? So let's just consider the binomial, right? The binomial distribution was, you can think of it as a probability of getting a certain number of heads. If you have a coin that has a probability p, and you have a certain number of trials. So you have two parameters. You have the number of, the head probability of the coin, and the number of trials. And now you want to know what is the probability of getting a certain number of heads. So the problem here is that if you increase the number of trials, then all of a sudden your domain, the set of possible values you can observe, will actually change, right? So if you have, if you have 10 trials, then the maximum number of heads is 10. But if you have 20 trials, all of a sudden you now have to consider numbers of trials up to 20. So the exponential family requires that the domain is not a function of the parameters, it's independent of the parameters. So that's why it says here, for example, the binomial with fixed numbers of trials, etc. So that's just kind of a small caveat, but otherwise these guys are also in that family. A couple points. So there'll be various different ways of writing the exponential family. They'll often, but for example, in the book, this n of theta is this eta of theta is just eta itself. But some of the kind of the notation might vary, so just kind of keep an eye on that. And this is the point that I just talked about. So this is again with the with the binomials. If you have more trials, then your domain changes. We can't have that. Okay, so let's keep going. The factorization doesn't matter. Vector parameters don't matter. Measure theoretic formulation. Okay, so this is kind of where we get to some of the really interesting stuff. So one of the key properties of this family is that it's the only one that has what's called a sufficient statistic. So a sufficient statistic you can think of as a summary of the data. And what's cool about with the exponential family is that this summary sufficient statistic will stay finite dimensional even if your data grows, even if you have, even as your number of data points grows, that size of your sufficient statistic will stay the same. So one example of this will be when you are trying to, when your data is coming from a normal distribution, and let's say you know the variance, but you don't know the mean. So normal distribution is in the exponential family, and now you're going to observe a bunch of samples of that. So you can have 100,000 examples, and now you want to infer what is the mean of that distribution. Well, it turns out that the mean, the way that mean depends on those data points, it can be summarized by just the sample mean, so just taking the average of the points you've already observed. So if you compute that sufficient statistic, which summarizes your enormous data set into a single value, that's equivalent. So that captures all the information that there is in your data set about the parameter you're interested in. So it's got this really amazing kind of compression property that's I guess very special, and only exponential family members have that. So, and let's see what they say here. So for exponential families, a sufficient statistic is a function of the data that holds all the information data x provide with regard to the unknown parameter. And so one of the ways they're going to explain that is, how are we going to figure out the parameters, right? Because we could, for example, compare theta 1 and theta 2. Those could be like, we have two guesses for what the means are, and we'll compare the likelihoods of those for our data set. And imagine we have one data set x and another data set y. And now it turns out that, for any data sets x and y, the likelihood ratio is the same if their sufficient statistics are the same. So that's kind of the definition of the sufficient statistic. It means that it doesn't really matter, for example, as long as the two, let's say, means that we computed in our example are the same, then the ratio of these parameters will be the same. So those sufficient statistics contain all the information that is relevant to determining, for example, in this case, whether theta 1 has a higher likelihood than theta 2. So that's kind of a really cool, that's kind of a definition of sufficient statistic. And for the exponential family, they have these kind of finite dimensional sufficient statistics that don't grow with the size of the data set, which is really cool. So the dimension of the sufficient statistics equals the number of parameters of theta, and encompasses all the information regarding the data related to the parameter, all of the information regarding the data relating to the parameter theta. And then it has some cool properties for when your data is IID, so when you're just sampling points independently, getting multiple samples that are all distributed the same way and are independent of each other. The sufficient statistic of a set of IID data is simply the sum of individual sufficient statistics and encapsulates all the information needed to describe the posterior distribution. So it's just saying that, yeah, you can just combine the information, the statistics of your data in kind of a very simple way. The natural parameter. Okay, so this is another interesting property. So eta is called the natural parameter. We kind of discussed that already. It's the set of values for which, whatever, the natural parameter space. It can be shown that natural parameter space is always convex. So the reason why that's useful is that when we're going to be often doing like maximum likelihood, and you want to make sure that you don't have multiple local maxima. And so when the space is convex, then that just means that any maximum you find will be the global maximum, and that's kind of a very nice property. So another very nice property of the exponential family. A of eta is called it. So this is A of eta is, I believe that it's the log of that function g that we have in the book, but it's just, the idea is the same. And the reason why this is important is kind of why I was mentioning it earlier, that it's not just a normalized, it is a normalizing constant, but it carries essentially lots of useful information. The function A is important in its own right because the mean, variance, and other moments of the sufficient statistic can be derived simply by differentiating A of eta. So that can be, that can be really useful. Okay, so now let's look at some of the properties. So exponential families have a large number of properties that make them extremely useful for statistical analysis. Okay, so why should we care about these guys? And in many cases, it can be shown that only exponential families have these properties. Okay, so examples. So exponential families are the only families with sufficient statistics that can summarize arbitrary amounts of IID data using a fixed number of values. So that's kind of what I was talking about, right? We have IID samples from this normal distribution. We're trying to figure out its mean. Well, you can give me 1 million data points, give me 10 million data points, and all I need, I can just summarize it with just the mean, a single value. It doesn't necessarily have to be a single value, but it's a fixed number of values which depend on the dimensionality of your natural parameters. This is a useful one. We'll see it also in the book. They have conjugate priors, so that means that your posterior will be in the same family as your prior, and that'll just be really nice for doing inference of the parameters and updating the parameters. It'll be really interesting. It's really useful. Let's skip the other ones. Okay. Cool. Now let's get to the examples. Yeah, so some technical points. But again, so here's the ones that we've already talked about: normal, exponential, log normal, gamma. Just a whole range of them are going to be in the family. The von Mises we talked about last time in the circular distributions bit. This is a bit about if some distributions are exponential families only if some of the parameters are held fixed. This is the fact that we don't want the domain to change. So it says, as a general rule, the support of an exponential family must remain the same across all parameter settings in the family. So the support just means the range of values over which is defined. That just goes back to that, the coin toss case. We can't have the number of trials being one of the parameters because that changes the domain, the support of the distribution. So the number of values we have to consider. But otherwise, so just keep that in mind. But otherwise, oh, and here's another one. So another set that aren't in the family. So in general, distributions that result from a finite or infinite mixture of other distributions, such as mixture models. We just saw mixture models in a previous video. And compound probability distributions. So those are the ones which are, so it's kind of this infinite mixing thing. Is a probability distribution that results from assuming that a random variable is distributed according to some parameterized distribution, with the parameters of that distribution themselves being random variables. So it's just a fancy way. Do you remember with the student's t, we were integrating a normal distribution against the gamma distribution? We thought of it as, we thought of the student's t distribution as an infinite mixture of Gaussians with the same mean but different variances. Okay, so it's basically saying that if you have infinite mixtures like that, or even finite mixtures like the Gaussian mixture models we saw, those will generally not be in the exponential family. So not every single distribution is in there, but a lot of the very useful ones are. Okay, yeah, and then here it's just, okay, so we're gonna do some examples in the books, so we don't need to go through this, but here's a table that just shows you all the, everything that you might need. This is actually good if you want to get additional practice with the exponential family. This is a good place to pick a distribution and then try to show that okay, its parameters are indeed what it says in this table, etc. So, but again, look, just re-emphasizing that point. There's so many distributions that are in this family. The gamma distribution, we've seen, beta distributions, so very useful. Okay, so scrolling. Yeah. So this is one of the properties that we'll see also in the book that you can, and we already mentioned it, that if you take that log normalizing function, you take its derivative, it'll give you the expectations or covariances or higher order moments of your sufficient statistics. So higher order moments and cumulants are obtained by this technique is often useful when t is a complicated function of the data whose moments are difficult to calculate by integration. So he's saying that, look, you can, for example, compute, take the integral of t over its probability distribution, but you can also just take the gradient of your normalizing function. Now, having this normalizing function itself can be quite difficult sometimes, but if you have it, then this gives you another way of computing these expectations, which is quite useful. Okay, so that's pretty cool. Yeah, let's skip some of these examples. Entropy. Okay, here is, I think, an example of where they've just made this thing more complicated than it has been by bringing in measure theory and things like that. But one of the really interesting properties of the exponential family is that it yields the maximum entropy distributions given constraints. So, for example, if you have kind of real value data, and you know that its mean is something and its variance is something, well, you might want to say, well, what is the distribution over that data that has the maximum uncertainty, right? It just incorporates those two pieces of information. Well, that distribution, this is the maximum entropy distribution, and it turns out to be the Gaussian distribution. So generally, these exponential family distributions can be defined as maximum entropy distributions under some constraints. And we'll get into when we look at the transcript with ChatGPT, we'll talk about why that's important. Yeah, this is just not very useful there. Okay, so now let's wrap up this part with the role in the statistics. So we already talked about this. This is important theorem. Among families of probability distributions whose domain does not vary with the parameters being estimated, again, only in exponential families is there a sufficient statistic whose dimension remains bounded as sample size increases. So here's let's just see what they mean. So suppose x of sub k, where k goes up to 1 to n, are independent, identically distributed random variables. Only if their distribution is one of the exponential family of distributions is there a sufficient statistic. So this is kind of some summary of those data points whose number of scalar components does not increase as the sample size increases. So it can be a vector or a single number, but whatever, its size will neither grow nor shrink when more data are obtained. And that's really quite remarkable, right? That's an amazing thing, amazing property to have. No matter how big your data set is, it's all you need for estimating the parameter you're interested in is that fixed size sufficient statistic. So that's really cool. We already talked about this conjugate priors. So we'll talk about it also in the chapter. So let's just skip this bit. Yeah, and that's about it. Oh yeah, and generalized linear models. We'll talk about this in the book a little bit. So exponential families can allow us to essentially kind of do regression, but over with a wider range of model. Let's say using the exponential family. So okay, so that's some reasons why it might be useful. And then I went and spoke with ChatGPT to see what it says about why it's useful. So let's kind of have a look at the conversation. So I said that, I know that lots of different probability distributions are members of the exponential family, and that members of the exponential family are maximum entropy distributions given the moments of the data. So that's what I was talking about. You know the mean, you know the variance. What is the maximum entropy distribution on the data? It'll be in the it'll be in the exponential family. In that case, it'll be, for example, Gaussian. Okay, so talked about conjugate priors. We'll see that as well. Generalized linear models. We just touched on that. Okay, so sufficiency. So this is what we talked about. Really important property. He's mentioning it again. That summarizes all the information about the parameter in the data, and this simplifies many statistical procedures, reducing data to a manageable form without losing information about the parameter. So this is essentially lossless compression of your data. And dimensionality reduction. The sufficient statistics often have lower dimensionality than the data itself, which can simplify both the computation and interpretation of results. Okay, yeah, indeed. Diverse range of distributions, we just saw that. So many of them are in that family. Parameter interpretation often have natural interpretations. Okay, then we'll see some of that actually in the example. So let's keep going. Log concavity. So this is kind of what we talked about, log concavity, or yeah. It's also sometimes called convexity. I think they generally mean the same thing, because you can either maximize or you can minimize the negative log likelihood, etc. But all of this means is that maximum likelihood estimation is well behaved. So that means it will have, and I think what they mean here is that it will have this one maximum. So you don't have to worry about local minima, etc. This is also very cool. Many problems involving exponential family distributions have closed form solutions. You might not really care about this in kind of like big applications, but when we're just working through and trying to gain intuition for what's going on in a model, how our parameters are being updated, this is really nice. Makes it and computationally efficient. Okay, so this is a cool one. So robustness to model misspecification. Due to their flexibility and generality, exponential family distributions are often more robust to deviations from model assumptions compared to non-exponential family distributions. Okay, so I mean, if that's the case, I don't know if that's the case, but if it is, you will almost always have the wrong model for your data. And what ChatGPT is saying here is that, if you're using an exponential family, then yeah, as it says, deviations from the assumptions will tend to be less harmful. Okay. And kind of connected to that, the statistical estimation procedures involving exponential family distributions tend to be more stable in large samples. Okay, and there's a couple of important ones as well. So I mean, they're all quite important, but the efficient information matrix often attains the Cramer-Rao lower bound, meaning that the MLE is an efficient estimator, having the lowest possible variance among unbiased estimators. I think we'll talk about this I think if we talk about this, we'll talk about it in the next chapter. So I think I'll just skip this for now. And information geometry, there seems some very deep. So information geometry is about looking at the geometry of parameter spaces, which is exactly what that says here. I'm just repeating that. And there are some really cool properties about it, but I don't know enough about information geometry to shed any light on that. So if you guys do, or you want to learn about it, I encourage you to do that. It sounds really, really cool. But yeah, and the exponential family seems to be very natural for that. Yeah, there's something you might have heard of a natural gradients. When you're doing gradient descent, if you essentially kind of do gradient descent in not the normal way, kind of the naive way, but if you kind of take into account these natural parameters and things like that, you essentially can improve your convergence behavior. So, for example, your gradients, maybe they won't spin around, your trajectories won't spin around as much. They will kind of go to the minimum more directly and more quickly. So that's kind of another way of, another useful property. Okay, yeah, so here I asked you to expand on the theoretical foundations, but I think the answers were useful, but I think I couldn't, I don't know enough about it to be able to tell you anything useful from that. Okay, where can I learn more? That was also pretty useless. Okay, yeah, so the other question I had was, and this is where some interesting answers come. So I asked, okay, so the properties of the exponential family are nice, right? So, that's pretty cool. We can all agree. But why is it that they come up so often in nature? Like, why is it they're actually useful? And I said, I could imagine, in a world where I construct a family of probability distributions that have all of those, let's say those nice information geometric properties, but that could just be like a fun mathematical exercise. So why do we see them so much in nature? Okay, and he actually gives some really interesting answers. So let's have a look at some of those. So, the reason why these distributions occur so frequently can be attributed to a combination of theoretical, practical, and sometimes even philosophical factors. So let's kind of have a look at that. Okay, so this is kind of the maximum entropy stuff. Natural constraints. So the maximum entropy principle states that given certain constraints, like known moments, like we know the mean or the variance of the data, the distribution that maximizes entropy, so is most uninformative beyond those constraints, belongs to the exponential family. And actually, now that he mentions that, so we'll see in the chapter that the very last section on this exponential family is talking about like different kinds of priors, uninformative priors. And I was wondering why he's put that there, but I think maybe that's the connection here, right? That essentially we want to say, look, we know a few things about the data, but now we want to set our priors so that it's just, it takes that information, but then it's as uninformative as possible. Well, such a prior will be in the exponential family. In many natural and physical systems, we often only have limited information, and the distribution that best represents this incomplete knowledge without assuming anything extra is one from the exponential family. So, another way of saying is the exponential family distributions are those that are most agnostic to what we don't know, making them naturally arise in systems where we only have partial information. So they don't, let's say they're not biased towards anything beyond what we've told them. Okay, now this is actually quite interesting. Give some interesting answers here. So sufficient statistics, we already kind of talked about what those are, but he kind of relates them to kind of natural processes. So natural processes often generate data where only a small set of statistics capture all the relevant information about the underlying parameters. Distributions in the exponential family have the property that these statistics are sufficient, right? Which means that they summarize all the necessary information about the data. So, you have this, it claims that natural processes often generate data where only a small set of statistics capture all the relevant information. And, then the distributions in this exponential family are those that are perfectly described by a small set of parameters. So there's kind of a connection there. In many natural systems, efficiency is key. The sufficiency property of the exponential family might reflect the kind of data compression that is naturally selected for in complex systems, making the distributions common in practice. So again, I'm not sure whether it's just kind of speculating fruitfully here, but it's kind of a really interesting idea that you can imagine. I don't know, like maybe you are some agent in kind of some natural environment and trying to interact with other agents, and that collection. So you are kind of finite, right? So you don't have time to kind of collect data infinitely. And so any setting where those agents, that environment can kind of co-adapt and co-evolve in such a way that just a finite number of parameters are sufficient for the agent to make optimal decisions might be favored. Complete speculation here, but it's kind of a fun idea to think about. Okay, so the central limit theorem. So, okay, this is an important one. So, explains why the normal distribution, a member of the exponential family, arises naturally as a limit distribution for the sum of independent random variables. So, in the real world, lots of the effects that we see are produced by sums of effects kind of adding up. And so that's why we see the normal distribution. So that at least explains why that distribution comes up a lot. And now this tendency towards normality underlies why many real-world processes exhibit distributions in the exponential family, especially under aggregation or averaging. And there are some extensions of the CLT which lead to other members like the Poisson distribution, etc. So I guess this part is just saying that this part is kind of explaining why specific members of the exponential family show up. And these are kind of, again, kind of similar. So in evolutionary biology, the strategies or traits that persist over time tend to be those that can be described by distributions that are stable under reproduction and inheritance, which often belong to the exponential family due to the inherent mathematical properties. So interesting idea. I don't know what it means, beyond that, but pretty cool. Again, this is more kind of along the lines that the Poisson process and exponential distributions show up. Like random events happening independently over time. So this is again explaining why certain members of the family show up. Simplicity in modeling, you can already imagine we touched on that. This is again quite cool. So in statistical mechanics, and I still haven't put up this video yet as of this filming of section, I think 1.6 or something like that, but it is mentioned in the book. So in statistical mechanics, the Boltzmann distribution, which describes the distribution states in a thermodynamic system, is an exponential family distribution. And remember that comes from the idea that we have this notion of the microstates describing your system, and there was the core idea is that at equilibrium, all of those microstates are equally probable, and that leads to this Boltzmann distribution describing those equilibrium systems, which is in the exponential family. So this connection to fundamental physical laws suggests that the exponential family might arise naturally wherever systems are in equilibrium or have maximum entropy under certain constraints. So that's kind of another reason why you might see this, these exponential family distributions showing up a lot, because if we're kind of dealing with systems that are somehow in equilibrium, but they have some constraints, maybe the average energy is is supposed to be something, because maybe, I don't know, you're connected to a heat bath, whatever it is. So under those settings, the exponential family is kind of what arises as describing those systems. Many natural systems can be described by minimizing an energy function, and the resulting equilibrium distribution often belongs to the exponential family. This is especially evident at thermodynamic equilibrium. Okay, so now lots of really important, including life, is not at equilibrium, but sometimes, we can describe things with equilibrium thermodynamics, and then the exponential family kind of becomes really important and describes those systems. This again kind of connects back to kind of the central limit theorem. So in high dimensional spaces, typical outcomes often concentrate around certain distributions, which tend to be from the exponential family. This concept, related to the law of large numbers, explains why certain distributions are typical in nature, even if the underlying processes are complex. So the idea being that you could have some very complicated underlying distribution, but if you have those effects kind of adding up independently, then the result essentially loses most of the information about that complexity and just comes down to something like the Gaussian, which has kind of a mean and a variance. So then the mixing essentially loses all the peculiarities of the things that went into the sum, aside from some of their very basic characteristics. And then that again has kind of an exponential family feel. You have a small number of parameters describing your system. As systems grow large, their behavior tends to become more regular, again for similar reasons, and can often be described by distributions in the exponential family due to their inherent instability and properties like sufficiency. Okay, so that was, I thought, really kind of interesting, kind of thought-provoking answers. So summary so often is a blend of their mathematical properties or connections to fundamental principles like entropy and sufficiency, and their prevalence in natural processes that optimize or stabilize certain quantities. These distributions offer both theoretical elegance and practical utility, making them naturally suited to describe a wide range of phenomena across different domains. So I think hopefully that was useful as trying to motivate why we might care about the exponential family. Now, as far as I looked in the index of the book, and he only talks about them, I think, after this point, I think in 2 other places. But I think it's just a cool family to know about and a cool concept to know about. So I thought it would be useful for us to kind of spend a little bit of time and just kind of get familiar with it and why we might actually want to learn about it beyond it just appearing, as a chapter in this book. So hopefully you found that useful as well. Please let me know if you did or if you didn't. And then I will see you in hopefully the next video, where we will now go and get back to the math and start working out how some of the distributions we covered, what their natural parameters, etc., their sufficient statistics are, and that'll kind of give you some kind of hands-on experience with this family. So hope you learned some stuff, and I'll see you in the next video. Thanks.